Yep. Hello, everyone. Welcome to the concluding part of lesson 1. In the last class, which is last Monday, we spoke about, we stopped at free electron theory, which is also known as Sommerfeld theory. And in that class, I extensively spoke about the relationship between the Fermi-Dirac distribution, the equations, and the graphs. So there are a few things that we should talk about before concluding that lesson, which I think it is economical to have this recorded and sent to you, other than having us waste time or having us try to rush over the lectures because of time. Okay. I think we stopped somewhere here. And sorry, I should have sent this earlier, but the week has been very full of events. Okay. In the last class we spoke about, I told you about different types of Fermis you can encounter in along the line while trying to study this course, which includes Fermi Surface, Fermi Sphere, and on this page I have 3 types of Fermis: Fermi wave vector, Fermi momentum, Fermi velocity. But there is nothing really strange about these Fermis. Along the line, you must have seen equations that is talking about Fermi or about wave vector, which is defined as root 2me over h cross square. If you have not seen an equation that looks like this, you must have seen the one that looks like eraser. And so then E got to you must have seen this equation one way or the other, especially in your 200 level. So this is the only difference here is that in this case we are using Fermi energy and Fermi wave vector, where the other items are constants. And so the same thing applies to this equation. Momentum is defined as h cross k, where p is momentum and k is wave vector. And talking about Fermi momentum is as good as calling this Fermi momentum, also corresponding to Fermi wave vector. And the same thing applies to the equation on velocity. So if you take off the Fermi subscripts, you'll have familiar equations. So the integral in equation 48, the integral in equation 48, this is the integral in equation 48, is telling us the total number of electrons in the system. Equation 48 is giving us the total number of electrons in the system, while equation 49 is telling us the total energy of the system of electrons. So when we know the total number of electrons in the system, it is very easy to determine the total energy of the electrons in the system. When you study these two equations, when you study them carefully, the only difference you see here is that this is having energy as a function of wave vector. So when we know the total number, I will multiply by the energy with respect to wave vector, we can determine the total energy of the system of electrons. So let's move forward. Now we know equation 48, which is so equation 48 the integral of equation 48 over a system, over a Fermi sphere of radius kf. You can see now that we are now defining another Fermi here. We are defining a Fermi sphere. The Fermi sphere, a sphere is just like a ball, and balls have radius. So the radius of this imaginary ball, which should have been r, we are calling it, okay, so let me draw it at this side, because I noticed, okay, so this is like the Fermi sphere, and the sphere has a radius, and the radius of this sphere, we call it Fermi radius, or better still, Fermi wave vector. The Fermi radius is the same thing as a Fermi wave vector, but when we are talking about a ball, it has a radius, and and if it is a Fermi ball, that means the ball should have a Fermi radius. And if it's a Fermi ball, this time around it's a Fermi sphere. A Fermi sphere should have a Fermi radius, and a Fermi sphere should have the surface of that sphere. Since it's a Fermi sphere, the surface should also be a Fermi surface. So whatsoever you can describe about a ball, or you can describe about a sphere, you can also describe about the Fermi sphere. If you want to say the center of the ball, if you call it anything, then for a Fermi sphere, it's Fermi anything. So at the center, from the center to the surface, is the Fermi wave vector, which is k subscript f. The surface of this Fermi sphere is known as the Fermi surface, and it is the surface that separates the filled states from unfilled states. So let's imagine this this sphere again. Let's have this sphere one more time. This is the sphere. This is the center. At the center, we can see that the energy level of this center is 0. But as electrons begin to fill it up, they begin to fill the lower energy levels gradually until they fill up to the Fermi surface. So when they fill up to the Fermi surface, all the energy levels within the sphere can be said to be completely filled at 0 Kelvin, while the energy levels above the sphere, because there are still energy levels above the sphere, there are still energy levels. Well, there are still energy levels outside this sphere, but they are empty. We still have energy levels outside this sphere, but they are empty, because at 0 Kelvin, the energy levels below the Fermi surface is completely occupied. Everything, this is the Fermi surface. Let's remind ourselves, every energy level below the Fermi surface is said to be completely occupied, while all the energy levels above the Fermi surface is said to be completely empty. Good. So now we are imagining it as a ball. So on the side, let me put something right here. And let's say we have it something like this as different energy levels. Let's use this one as EF, as Fermi level. And we have some energy levels below EF. Let's also see we have some energy levels even above EF. So the red energy levels are above the Fermi level, while the blue energy levels are either at the Fermi level or below the Fermi level. So this line, the Fermi level here, is equivalent to the surface of this sphere. And all the lines underneath the surface down to the center of the sphere is equivalent to all the lines below the Fermi level. And the red dashed lines outside the sphere is equivalent to the red lines that is above the Fermi level. So the picture I want you to paint in your mind is to note that these levels are occupied by electrons when the system is at 0 Kelvin, but anything above it is empty. This is occupied by electrons at 0 Kelvin, while this is empty, not having any electron. It's available, the energy states are available, but they are not being occupied by any electron. So the same thing, so if you have this well programmed in your mind, you should be able to also picture a ball such that at the center of the ball, we have lower energy levels which increase until we get to the surface. And even outside the surface of the ball, there are still energy levels. But the difference is that at 0 Kelvin, from the surface of the ball down to the center of the ball, they are occupied by electrons. But anything outside the surface of the ball, it is empty. And that particular ball in question is called the Fermi ball. But let's call it Fermi sphere. Let's talk international, the Fermi sphere. And the radius of that ball, sphere, radius of that sphere is Fermi radius, which is equivalent to Fermi wave vector. So whatsoever you can talk about that sphere, you can talk about it as the Fermi equivalent. So from equation, let me wipe this off. So from equation of 48, we can come to get our equation 50, which tells us the number of states that is completely filled. So at 0 Kelvin, the states below the Fermi surface is completely filled, while the states above is empty. So this equation 50 is telling us the number of states that is the number of electrons that is below the Fermi level. So, and wherever we have a small n is like number density. When we know a particular number, the number of electrons in this case, we can also determine, if we know that this number of electrons are occupying a certain volume, we may be interested how many electrons are occupying a specific volume. So that's number density, that is the number divided by volume. So, and that leads us to some other equations. So what we have here is in equation 51 and 52 is same as what we had in right up here as Fermi wave vector. Okay, so let me rewrite this one down here. KF. Sorry. KF. So I'm trying to figure out so from this expression, we can bring out our small n. From equation 50, we can say our small n, which is equal to big N divided by V. So it's as good as dividing the right-hand side by V is equal to, oh, okay, I think I should be writing in that corner, N equal to n over v is equal to 2 over 2 pi cube times 4 over 3 pi kf cube. If you look at this expression I've just written, or what we have here, 4 over 3 pi kf cube, if you remember what they taught us in primary school, you note that this looks like the volume of a sphere, 4 over 3 pi k cube, and you should have seen it all along in our equation 48, if I'm not mistaken. So when you take this particular expression, you can make kf the subject of the formula and obtain equation 51. And from equation 51, you may decide to put kf into kf into this, replace kf right here in this expression we have above, and you would have a convenient equation 52. So you can play with it. Every equation here has, they are all below your level. So don't be scared of seeing any equation. They are things, they are all interrelated. So let's move ahead. So now let's move on to the business of the day, which is the electronic heat capacity. Because we have we said earlier in the early part of the class that one of the failures of Drude theory was that they used a specific heat capacity meant for monatomic gases as that of electrons, which it's an assumption anyway. But when it's when the theory failed to predict some things it should they expected it to predict, then that is when they now start going back to the assumptions to say that this could be responsible, which includes the specific heat capacity of electrons wasn't used, maybe because it wasn't known. That is why they used that of monatomic gases, just to estimate. But now we're talking about the electronic heat capacity, the specific heat capacity of electrons, not monatomic gases. And that starts with us going back to our equation 48, which has been recalled right here. And from that, our equation 48, from the equation 48, it can, we can, it's an integral with respect to wave vector. And we can change this wave vector because right now we are more interested in energy than wave vector. And now we have an expression here which relates wave vector to energy. So we'll be interested in changing everything that looks like wave vector in this expression. We'll be interested in changing it, or let me just use converting everything that looks like wave vector here to energy terms. So to do that, we substitute root 2 mu over h cross square for k in equation 48. So equation 53 is just like equation 48. It's just that in equation 53, there is nothing like wave vector anymore. We have somehow silenced wave vector, and we have just like a change of formula, whatsoever you can call it. But this is just basic mathematics where you change everything that looks like K to E, since you have the relationship. And so I expect you to read, go through this footnotes. I think yes, I remember. Yes, that footnote. It will guide you if you want to practice how you convert this particular expression to this expression. You need to go through this footnotes 40 if you have challenges doing that. So now again, we have the number of electrons in the system as n. The total energy of the system should not be a problem because the only difference will also be the energy term. This is the only, the epsilon here is the only difference you will see between equation 53 and 54. G of epsilon d epsilon is the density of states per volume. Density of states per volume. And is defined as the total number of eigenstates with energies between epsilon and epsilon plus the epsilon. So there is an energy level called epsilon, and when you move ahead, you may call this epsilon. When you move ahead, epsilon plus the epsilon. So the number of energies, the number of states, or the number of states with energies between epsilon and epsilon the epsilon. So this is not the first time we'll be talking about density of states, but I think the first time we spoke about density of states, we were talking about wave vectors. We're talking in terms of wave vectors, but now we are talking in terms of energies. We're talking about electrons having energy between this range. So how many of these electrons have energies between epsilon and epsilon plus the epsilon, just a range of the epsilon. So the density of states is defined in equation 55. So one step leads to the other. So the density of states, so like we had before, is given in equation 55. So we can treat equation 54, which tells us the total energy of the system. Equation 54, which tells us the total energy of the system. We can treat it with the assumption that when the temperature is almost zero, when the temperature is about zero, that the Fermi energy is approximately the chemical potential. This is a good assumption to me. And with that assumption, the kinetic, with the assumption, it can help us to estimate the energy of the system at finite temperatures. Okay, so let's okay. Okay, I positioned this here earlier. Yep. So we can treat the energy of the system with the assumption that at when t is almost zero, that when t is almost zero, that the Fermi energy is approximately the chemical potential. And I've said earlier in the previous class that the Fermi energy is a step function. Sorry, the Fermi Dirac statistics gives a step function when the temperature is zero, and the step function smears out as temperature increases. So at finite temperatures, when that is when the temperature is greater than zero, and it continues to increase, the step that we have in the Fermi Dirac distribution begins to become slant. It slopes, and the step fades out. So from that assumption, we can come out to bring out an approximate value for energy at finite temperatures. And the energy at finite temperatures will be as good as saying what is the energy at temperature T equal to 0, and what is the energy at as the temperature begins to increase. So there are some terms we have not seen before, which have been introduced just for as a result of the assumptions and approximations. One of which is to say that V subscript G of EF is the density of states per Fermi surface, while G is the density of states per unit volume. And so, and Vg of EF kBT is the number of particles close to the Fermi surface. So everything here, V of G is defined here. Vg of Fermi energy, kBT, is defined as the number of particles close to the Fermi surface. So when we know the number of particles close to the Fermi surface, I will multiply it with multiply it by an energy term. Then we get the energy of the particles close to the Fermi surface. So, and when we are talking about excitation of particles, it is those that are closer to the Fermi surface that actually gets excited, because at 0 Kelvin, there is nothing like excitation. It's above 0 Kelvin that we begin to talk about excitation. So as temperature increases, excitation also increases, and when the excitation increases, that is when will be the step function smears out. That is when we begin to see an area that is below the Fermi energy now fading off, now appearing above the Fermi energy level. So the major point here is that this is the number of particles close to the surface. It's an estimate, and multiplying by energy term gives us the energy, the total energy of the particles about the Fermi surface. And the pi, this gamma bar is a constant described as pi square over 3. So from this approximation, it can be said that we have an approximate value of E, that approximate value of energy with respect to temperature. And now coming down to equation 57, when we have done this several times, well, we know the energy of a system and we differentiate with respect to temperature, then we have the specific heat capacity. When we know the energy of a system and we differentiate with respect to temperature, then it can be said that we have the specific heat capacity of that system. And now the energy of the system. What system? System of electrons, not a system of monatomic gases. It's now a system of electrons. So now we know the energy of a system of electrons. And do we know the energy at 0? We also know the energy at finite temperatures. So what is interesting here is the change in energy with time. And that leads us to differentiating the expression here with respect to temperature. So, and when we do that, we have gamma bar, which we've said to be a constant. Things like this, are usually introduced when you are trying to fine-tune a result, and you see that what you are having, let's say you are expecting to have something in the order of 4, 8, or let me use 14, 16, 18, but you are expecting 28, 32, but you're having 14. 16. Then you introduce a term, and you can call it alpha if you like. I call it 2. And the 2 will multiply the 14 you have obtained to get the actual 16 you should have gotten. So, and that leads us to what? It leads us to saying that the E, the T, is gamma bar 3/2 nkb, then temperature over Fermi temperature. Then if you look at this expression, we can call this the specific heat capacity for electrons. If you look at this carefully, 3/2 nkb, this is the specific heat capacity for monatomic gases. Specific heat capacity for monatomic gases, ideal monatomic gases. But now for electrons, according to what we have seen so far, it is now being multiplied by another term, which is T over T subscript F, temperature over Fermi temperature. So this is the difference, that this is the term T over TF is a term that wasn't included initially while Drude was busy trying to use specific capacity of electrons. When he needed specific capacity of electrons, he used that of monatomic gases, and this is the difference. This is the term that was missed out. This gamma, when we try to estimate this gamma, it's as good as saying about 3. So, but this is not the main difference. The main difference here is T over TF, which is 0.01. It's very small. It's about 0.01. And that says that the specific heat capacity of monatomic gases is about 100 times greater than the specific heat capacity of electrons. So this is like saying that Drude overestimated the specific heat capacity of electrons by a factor of 100. So this table shows, table 1.3 shows the heat capacity coefficient of some metals. And when you go through them, it's some are very good, while some are very wide apart. But most of them are at least manageable. If this is experimental and this is the computed using Sommerfeld's theory, or using the free electron theory. So with the knowledge that T over TF is about 1/100, then we can re-examine Drude theory. So Drude theory, like we have said before, predicted Seebeck's coefficients. It predicted Seebeck's coefficients with as this, which is large by 100. So it was large by 100 if they used the original C for electrons and not that of monatomic gases. The 1/100 here would have cancelled this 100. Then they would have gotten something more reasonable or more realistic than what they actually got. And Drude theory was wrong because specific heat capacity for classical gas was used for electrons. So that's just what I've just said. You see is 3/2 kb for electrons. Sorry. CV is 3/2 kb for monatomic gases, but we have to multiply by 1/100 to have an approximate value of specific capacity of electrons. So this CV here, if they had used that of electrons and not that of monatomic gases, then Drude theory would have predicted Seebeck's coefficient more reasonably, but it predicted Seebeck's coefficient wrongly by a factor of about 100, which we have now seen the reason why Drude theory failed to predict Seebeck's coefficient reasonably. Drude theory calculation of thermal conductivity. This is kappa, which is thermal conductivity, 1/3 n CV V lambda. CV used was large, just like we have just said here. The CV used in Drude theory is large because the CV used in Drude theory is the CV for monatomic gases. So just like we have said earlier, the CV used over there by Drude, the CV used by Drude is large by 100. And when you look at this expression, the CV here, which was used in calculating thermal conductivity for Drude, is also shows that one mistake was done here. The CV used here was also that of monatomic gases, not that of electrons. So I think it's good I write this out. Our kappa is equal to 1/3 n CV no velocity and lambda. That's the scatter length. And we've okay, I go over it again. This is kappa, thermal conductivity. In the computation of thermal conductivity by Drude theory, CV was overestimated. CV used was that of monatomic gases, not that of electrons. So this was too big by 100. This was like in Drude theory, this is times 100, about times 100. And the only good thing about this thermal conductivity is that the velocity, the average velocity calculated was too small by the same factor. So that tells us that the CV calculated was times 100, while the average velocity used was like times 1/100. Therefore, when you have a situation like this 100 will cancel 1/100, and you end up having the correct answer, because two errors coincidentally cancelled each other to favor the course of action, which is the ability to predict thermal conductivity correctly. So Drude theory predicted thermal conductivity correctly because two errors were made coincidentally. So, and because of those two errors, that is why Drude theory was able to, those two errors that worked hand in hand, that is why Drude theory was able to agree with Wiedemann-Franz law. So let's move straight to magnetic spin susceptibility. Magnetic spin susceptibility, or also known as Pauli paramagnetism. And what this aspect is concerned with is the property of free electron gases. How do they respond to externally applied magnetic field? So when we've must have done something like this in some elementary physics, that when electron is entering a magnetic field, the path is curved by the as a result of the magnetic field. When the magnetic field, most especially when the magnetic field, direction of the magnetic field is perpendicular to the direction of the path of the direction of the electron travel. So the motion of electron is curved due to the Lorentz force, due to the presence of the magnetic field. And there's also another thing that happens. Electron spins flip over due to magnetic field, which changes the magnetic moments of the electron gas. So in the next lesson, we'll be talking about spins as a property of some elements, as a property of elements anyway. But for now, let's just see it as electrons. Well, they spin up, so they may spin up or spin down. Electrons can be said to be spinning up or spinning down. And when we are talking about orbitals, energy levels, when we talk about Pauli's exclusion principle, then we should be talking about we said, or we can say, two electrons are occupying the same in the same energy level. One is spin up, the other one is spin down, and it's usually denoted as, say, using arrows to say spin up, spin down. So when you see an arrow pointing up, we are referring to spin up, and when we see arrow pointing down, we're referring to spin down. So when two electrons are occupying the same energy level, that is only possible because one is spinning up while the other one is spinning down. They are occupying the same energy level, but somehow they are not exactly in the same state. So let's move ahead. I hope it will make clearer sense as we proceed. The Hamiltonian is defined as equation 58. Equation 58, which is the Hamiltonian, is showing us this term should be familiar, like a kinetic energy term, and a term that is as a result of a magnetic field, the presence of magnetic field. So from equation 58 is defined as G bar is the G factor of the electron, which is 2. B is the magnetic field vector. Sigma is the spin of electrons. Oh, thank you. I forgot to mention spin of electrons. I said I spoke about spin ups, spin downs. The spin ups are usually referred to as plus 1/2, while the spin downs are usually referred to as minus 1/2. And U subscript B, mu subscript B is the Bohr magneton, which is Bohr magneton, which is defined as EH bar over 2 ME. ME is the mass of electron. Normalized mass constant. E is charge of electron. So in the magnetic field, the energy of an electron with spin ups or spin down is given as equation 59. So in the magnetic field, the energy of an electron with spin up or spin down is given as equation 59. So And in this scenario, we are referring to spin-ups as the electrons that have the same direction as the applied field. The electrons that have the same direction as the applied field in this scenario is what we are referring to as spin-up. Because I tried painting the picture with my cursor to say spin-ups and spin down. So as I'm showing spin-up, if you are looking from another angle, you may have seen it as turning anti-clockwise. So it depends on how you are viewing it. Are you viewing it with a mirror, lights like that? So, but the major thing is the reason what we have chosen to be our spin up are the electrons whose spin aligns with that of the applied magnetic field. So now we have two equations here. This is the energy as a function of wave vector and spin. Wave vector as a function of wave vector and spin. So the energy is h square k square. This is, we are familiar with this. We have spoken about this today. Plus mu b b. So there is a difference here. The only difference between these two equations is that this is plus and this is minus. So looking at this equation, it means that this is having like higher energy level compared to the spin downs. The spin ups is having higher energy level compared to the spin downs. So the energy levels that are lower are known to be preferred. Things nature prefers to occupy lower energy levels. When you are pouring water in a cup, the water sits at the bottom of your cup and it fills up to the brim of your cup. When you are pouring water in the cup, it doesn't start from the top. It doesn't start from the top filling down to the bottom. It starts from the bottom filling up to the top. And that is nature for you. The lower energy levels preferred to be occupied before the higher energy level. So let's just take this in mind as we move further. So we cannot talk about the magnetic susceptibility without talking about the spin magnetization. And the spin magnetization, or the moment per unit volume, is defined in equation 60. And it's this spin, the moments per unit volume. So the moment is the EdB per unit volume. And it's also defined as 1 over V, that's per unit volume, the number of spins, spin-ups, minus the number of down spins, so the number of electrons spinning up minus the number of electrons spinning down. And remember, the spin-ups are the ones that align with the direction of magnetic field. And we've said the energy of spin-ups is greater than that of spin-down. And the energy that is lower is preferred in nature. And B is Bohr magneton, we have defined in earlier. And when you, so all, if we can know the number of spin-ups and the number of spin-downs, then the simple arithmetic, number of spin-ups minus one number of spin-downs times B divided by V gives us the spin magnetization of the system. So when magnetic field is applied, there will be more spin downs because the down spin indicates lower energy. We have seen that in the previous equation. So let's look at this graph, which tells us the effect of magnetic field on the occupation of electronic states. The effect of magnetic field on the occupation of electronic states. So this graph is this number one. This graph is divided into two. this aspect is telling us when magnetic field is zero. When B is zero, when magnetic field is zero, is the left-hand side of this graph. And when magnetic field is not zero, when it is non-zero, that is when we are talking about this. So let's first face this aspect of this graph where magnetic field is zero. When magnetic field is zero, then our electron needs not bend due to Lorentz force. It will just take its normal course as if there is no disturbance. When the magnetic field is zero, the assumptions that we stated in the early part of the lecture, or the early part of this section, would need not apply, because there is no need for Lorentz force and no need for bending. So this graph, this axis is telling us the density of electrons. So let's just let's just use the number of electrons, number of spin-ups. That's the density of spin-ups. Okay, I was saying something. When B is zero, electrons would not be cuffed, and electrons will not flip over. Since magnetic field is not applied, electrons would not flip over. So now let's move back here. So let's call this the density of the number of electrons. Let's use G of E as the number of electrons that is being occupied. And this is spin ups, this is spin down. And this is like a graph of the number of electrons for a certain energy. And this is the energy. And this is Fermi energy. The shaded part here is telling us that all the energy levels below the Fermi energy is occupied, while the white part is showing us that there is no electron here. So the shaded part is telling us that this place is occupied by electrons. So the point we should try to get here is that for spin-ups and spin-downs, the number of electrons, the number of spin-ups below the Fermi energy is equal to the number of spin-downs below the Fermi energy when there is no magnetic field, when there is no external magnetic field applied. The number of spin-ups is equal to the number of spin-downs. And at 0 Kelvin, all the energy levels below the Fermi energy is completely filled, while those above it is empty. So that's for when magnetic field is zero, when magnetic field is absent, when external magnetic field is not there. So now, when magnetic field is present, when external magnetic field is applied, something different happens. When you look at this graph, you notice that for the fact that external magnetic field is applied, this graph is shifting forward by a factor of mu B. Mu B has a unit of energy. When external magnetic field B is applied, mu B is shifts the graph shifts forward by mu B, and when it shifts forward, you'll notice that nothing should when it shifts forward, the original shape that we add here should be the original shape, just like we have the shape we have here, the area under the graph here. The area under the graph here is also the area under this point, following the dotted lines coming down straight here. But because this is Fermi energy, no state is permitted to stay above the Fermi energy at t at t equal to 0, no state, no electron is allowed to occupy any state above the Fermi energy. So in short, this place becomes empty. That means some electrons that were spinning up are no longer spinning up. They will occupy energy levels from this point, B, up to the Fermi energy, and that is all. And when we look at the spin down electrons, the number of spin downs, the graph we have here, the area of this shape is also equal to the area from here to this point down here. So one thing we should notice that for the fact that magnetic field is applied, the graph of the spin downs shifts to the left by a factor of well, it shifts to the left by, not a factor, it shifts to the left by mu b. Mu b is Born magneton, while b is the magnetic field that is applied. B is the magnetic field that is applied, and it shifts to the left. But when it shifts to the left, the original electrons that were occupying this point, this shape, the original electrons that were occupying this shape will also be the ones that will occupy this shape from here. Look at the line I'm following, especially this line. But something different will also happen. The electrons that were, let me say, evicted from this place, or that decided to decamp from this place, will now come and fill this shape. The electrons that left the spin-ups will now come and fill this place. So in the presence of magnetic field, we will have more spin downs and we would now have less spin-ups. So some electrons that were spinning up before will begin to spin down because of the presence of magnetic field. So that is a property we should note when we're talking about spin magnetization. Some electrons that were spinning up will begin to spin down in the presence of magnetic field, noting that the electrons we've defined as spin-ups are the ones whose direction of spin aligns with that of the applied magnetic field. So equation 61. Equation 61 is telling us that it's like an equivalent of the magnetization equation that we have here. So equation 60, equation 60 and equation 61, they are actually saying the same thing. So you can look through them. This is the MOB you have here is also the same. One of the MOB you have here. So is this as good as saying, if you want to play with this equation, you can say G of E, F, MOB, B. And one of the MOB is the one I circled up here. And the other one is as a result of we talking about this particular equation. The other one is as a result of this particular equation, equation 59. So this equation 59 is telling us the energies of spin-ups and energies of spin-downs. And at this point, we are interested in the number of spin-ups and the number of spin-downs. So when we determine the number of spin-ups and the number of spin-downs, which when you read this paragraph, it should shed more light. But we now end up relating equation 60 to equation 61 to say that the magnetization is defined as equation 61. So, well, So magnetic susceptibility is defined in equation 62, which to me I feel is straightforward. But if you have any questions, please do not hesitate to ask. So the free electron theory considers the fact that electrons are fermions. Yes, that's one of the differences, one of the advances of the free electron theory, that electrons are fermions. You cannot just pack all of them together and be treating them as if they are just gases. They are fermions. They occupy energy levels, that and that and that. But it did not consider the fact that these fermions interact with one another. So that is one problem that is waiting also to be to cause problems ahead. So Columbic interactions, we did not even talk about Coulomb's law. We were just talking about electrons, electron filling a sphere. We did not even talk about Columbic interactions. And also the free electron theory failed to explain the presence of positive charge carriers in the Drude theory. Also, the specific heat capacity of electrons in free electron is superior to the Drude theory. The value is still wrong by a factor of 10 for some metals, but it is important to consider the peculiarities of, it is important to consider the peculiarities of chemical nature of elements. So we have been talking about materials in general. We have not really spoken about the chemical nature of elements. The way we talk about sodium should be different from the way we talk about chlorine. And this would lead us to the end of this lesson. So tomorrow we should meet and talk about structure of materials. So we'll talk about periodic table, chemical bonding, and I hope we can move very far when we meet. So please do not hesitate to let me know if you have questions about what we have spoken about so far. And this is the end of lesson 1 anyway. And I think we have moved fair enough. Lesson 2 should not take as much time as lesson 1. And as the course goes on, I hope it will become more interesting. We should have some, we should be talking about things that we can relate to directly, unlike some abstract things we are currently talking about. So see you later in a few hours when we'll meet again. Bye-bye. And boom. And